Alright, so we were in the middle of constructing spherical harmonics. Actually, we wrote down the answer, the explicit answer, or at least a differential recursion relation for the spherical harmonics. Right? So let's just remind ourselves there are at least two methods that we have seen so far. One is to use the definition of spherical harmonics as the homogeneous polynomials of degree L that satisfies the Laplace equation, right? And then in terms of using x plus, x minus, and x3 written in spherical coordinates, you can use it to directly construct these spherical harmonics. The other way is through the Lie, essentially motivated by the Lie algebra of SO3, of the rotation group. Right? What we realized was that there's a pair of raising and lowering operators that we can use that to construct these spherical harmonics. And the way to go about that is to recognize that the raising and lowering operators, in particular the raising operator acting on the highest n value, which is L, this has to be 0, and the lowering operator acting on L and minus L, which is the lowest n value, that also has to be 0. Okay, so this is the key point that we use to then construct the YLL and Y minus L. Okay, so in fact, these mean together means that YLL theta phi, which remember is simply the position space representation of LL. This guy is proportional to sine theta to the Lth power, and then because the n value is L, is e to the I L phi. Okay? And YL minus M can show from the same argument is also proportional to sine theta to the L, but this n value is now minus I L F phi. And in fact, once you've gotten, you don't really need both. Once you've gotten one of them, in principle, you can go ahead and just use the lowering or raising operator to get the other states. Okay? So let's continue from there. So I know I've written down the answer already, but let's in fact step through it more systematically, because the last time we did it, we were kind of in a hurry. It was, yeah. So let's, in fact, step through that derivation. So, in fact, where we were the last time is that we had an angular expression for J plus and J minus. So let's write that down. So theta phi of J plus minus of psi, where psi can be anything, is e to the plus minus I phi. So this is easy enough to remember. If this is supposed to raise or lower the eigenvalue by 1, surely you need this plus or minus because you know that this is actually the eigenfunction of J3. Right? This is the eigenfunction of J3. So this would be plus or minus d theta, and then plus I cotangent theta. Oops, d5. That's minus d theta, I cotangent theta, and then acting on theta phi psi. Yeah. I'm going to suppress the R dependence. Of course, for a physical wave function, it's going to depend on R as well, but for now we don't need it, so I'm just going to suppress it. So what we've already seen is that if you plug this in, you will get that answer, right? And what you'll find is that you can normalize this guy. So once you've normalized it, you will find the following. Okay, so you will find, in fact, that YLM, let me be more to be normal. Once you normalize it, and by that I mean you square it and you integrate over the sphere, and you demand that the integral gives you 1, that will tell you that YLL would in fact be equals to minus 1 to the L. This is a phase convention, divided by 2 to the L factorial, and then you have square root of 2L plus 1 over 4 pi, and then you do square root of n plus L 2L factorial, square root, and then e to the I L phi over sine L theta d cosine of, I'm sorry, there's no point. Yeah, okay. Yeah, that's it actually. So this is sine of L theta. Okay. Yeah, so this is a sign convention. So there's always a phase convention. So let me just write that down. So note, so YLM has a phase convention because remember that this is an eigenvector. The eigenvectors have a phase that you can never determine because you square it, and all it needs to do is just integrate to 1, right? So whenever you use YLM, make sure you check whatever source that you're taking your expression from. Make sure you check the phase convention, right? The normalization is the same, right? But the phase convention may not be. Okay. Now the claim is the following. Find it darker. So the claim is the following, that we can choose for m greater or equals to 0, meaning for all the non-negative m's, we can choose YLM to be minus 1 to the L divided by 2 to the L factorial, and this will be square root of 2L plus 1 over 4 pi, and then there's a square root of L plus m factorial divided by L minus m factorial, and then to the I L phi over sine n phi, theta, and then d cosine theta acting L minus n times on sine squared. Sine squared is 1 minus cosine squared theta to the L power. Sine squared to the L power, I mean. Okay? That's the claim. And this is where we left off the last time, but why is it true? Right? So the way to show this is, of course, by induction. So we already know that when you set m equals to L, it recovers this solution, right? And I'll leave it to you to verify that when you integrate this, you in fact get this normalization. Right? These guys are just normalization. But the question is, why is it for arbitrary m, non-negative m, this is what you get, right? So if you were to prove it by induction, all you have to show is that this would take the same form if you choose to suppose the nth case is true. Yeah? So I want to go to n minus 1. This is now the nth case. So now let's look at what the n minus 1 case is. But we have to be careful with the normalization. So the first thing to recognize is what are these guys when you apply them to an eigenstate? Yeah, that's something that we have not derived. So let's make sure we visit that statement first. Okay? So remember that the normalization of J plus minus dagger, not normalization, the product of J plus minus dagger times J plus minus is given by J squared minus J3 squared and then minus plus J3. Okay? And so when you take the, when you're applying J plus or minus on Lm, you can at least find out up to a phase, you can find out what the answer is by taking the norm of this guy, right? So the norm will not allow you to get the phase, so there's always a choice that we make. But at least we can find out what the norm is. And the norm of this guy is, of course, just J plus minus dagger, and then Lm. And what is this guy? This is now Lm times J squared minus J3 squared minus plus J3 acting on Lm. Okay? And because these are all eigenstates, these guys are eigenstates of all these operators, you can write down right away that this is L times L plus 1. That's the eigenvalue of J squared in 3 dimensions. This is minus m squared, and then m plus or minus 1. Okay. That's what this is. Minus m squared minus plus m, which is that here. On the other hand, if J plus or minus Lm is going to give you some constant, which I'm going to just call plus or minus. And you know what it's going to do? It's just going to add or subtract by 1 the m value. Okay, so this is going to allow us to figure out what is c plus minus. So what's going to happen is that we've already figured out what the norm is. We figured out what the norm is. This is given by L times L plus 1 minus n cos minus 1. And that, in fact, is of course just a norm of this guy, which is just c cos minus squared. L n cos minus 1, L n cos minus 1, of course, which is 1. Right? That's what we define to be 1. So therefore, we often just take the phase to be just a positive square root. But remember that m times m cos minus 1 is always less than this guy, because L is the maximum value, right? So remember that L is greater or equal to m. So therefore, you can just take the positive square root. So just take square root of L times L plus 1, oops, I'm sorry, L plus 1, and then minus n times n plus minus 1. Okay, so positive square root. Again, remember, because this is the inside is always a positive number. And therefore, we can just summarize that. Therefore, j plus minus acting on by the way, this can also be factorized, which will come in later. Square root. You can show that this is the square root of L of minus plus m, and then L plus minus m plus 1 square root. Okay, so therefore, j plus minus acting on Lm is in fact just square root of L minus plus m, L plus minus m plus 1, and then multiplied by L n plus minus 1. Okay, so this was the number that we didn't know. That was the number we didn't know, but now we know, just from the norm of it. Right? So in other words, we choose phase to be 1. It is a choice, right? Which I will continue to stick with. But it is a choice. It's always remember that it's always a choice because the eigenvector is always ambiguous up to a phase. Or rather, it's only fixed. It's fixed up to a phase. Okay. So how is this related to that? Because now that we know this, let's in fact use this fact, right? So j, now in particular we want to know j minus Lm theta phi, and this is in fact, as we just discovered, is given by square root of L minus m, I'm sorry, plus m, and then L minus m plus 1, and then this is given by theta phi Lm minus 1. Okay, this is what it does to it, but this in turn has this angular derivative operation, right? This is given by, at the same time, e to the minus I phi, and then minus d theta plus I cotangent theta d phi acting on YLM of theta phi. Okay? So therefore, after you've done this operation, you just divide by this, and you should get, in fact, we can replace this with YLN minus 1 theta phi. So so once we've done this differentiation, you can get the next guy. So that is easy enough. And hopefully you can see the power of the algebraic reasoning is that it gives you these clean results just from algebra. You don't have to solve complicated differential equations, which is the case which is what you do if you do electromagnetism. That's how you usually do it in Jackson. Right? Okay, so let's do it. So remember, we are going to assume that the nth case is true, and all that we're doing here is because to set things up so that we can now take this derivative. Okay, so let's in fact see what does this derivative do, and of course all these are just normalizations. And what I really just need to do is figure out how does the derivative act on this guy. Okay, so what I really have is that I have e to the minus I phi, and then I have minus d theta plus I cotangent theta d phi acting on e to the I m phi over sine theta m. And then this guy, I'm just going to say is a function of cosine theta. Yeah? Because everything here, I'm writing it as a function of theta. So let's do it. Okay, so this is now e to the I phi, e to the I d phi acting on that will just bring down I d phi will just bring down let's do it. I squared m cotangent theta, right? That's what it does. And then this guy will now combine with this and give you e to the I n minus 1 phi, and then now you have minus d theta plus I squared n cotangent theta acting on 1 over sine n theta f of cosine theta. And then the rest is just differentiation, right? So e to the I n minus 1 phi, and the main problem is the differentiation of this. So let's just do it step by step. So this is sine to the minus m, so you get plus m, and then you get sine theta minus m minus 1 cos theta, okay, times f, and then plus, of course, the chain rule, sine theta to the minus m, and then f prime of cosine theta times minus sine theta, and then minus m squared, let's go to the next slide, minus m cotangent theta times sine minus n theta f. Okay? So let's combine things and see what do we get. So e to the minus I, e to the I n minus 1 phi, and then we have, let's combine the signs first. sine to 1 over sine to the n plus 1 theta. Actually, what I want to do is I want to show that it gives me minus 1. So what I'm going to do is I'm going to, and then we have f prime of cosine theta. What I need to show is that it cancels out, right? So this guy has to cancel out. So let me just write that down first. So this, in fact, tells you it cancels out. Why? Because it's n over sine theta to the n, and let me pull out a sine. So sine to the n minus 1, at minus n minus 1 is sine to the n theta times sine theta in the denominator. And then you have a cosine theta times f, that's over here. But this guy is minus m over sine theta to the n, this guy over here. And then cotangent theta is nothing but cosine theta over sine theta times f. Okay, so these two terms cancel out, and what you're left with is this term here, which is minus sine theta over sine theta to the m. So it's f prime over sine theta to the n minus 1 power. Okay. Very good. So therefore, we have minus the I n minus 1 5, and then f prime, which now I'm going to write as g cosine acting on f, and then the whole thing divided by sine to the n minus 1 theta. But remember, what is f? F is actually this guy over here. Okay? So let's in fact write that down as well. So f is L minus m and then plus 1. Okay, but L minus m plus 1 is just L minus m minus 1, acting on 1 minus cosine squared theta to the L. That is f, remember. This whole thing is g cosine theta acting on f of cosine theta. Okay? So what have I shown? I've shown that I think I messed up this number, right? So this is n. I wrote it correctly over there, but over here I didn't. Yeah, so what have we shown? We have shown that if the nth case is true, the nth minus 1 case, at least this part of it, is also true. Right? Because if the n minus 1 case is true, all I have to do is just shift all the n's here by minus 1. And that's exactly what I have over here. Minus 1, n minus 1, n minus 1, and n minus 1. Okay? And what remains is to show that the normalization is also right, up to a face. Okay? Up to a face. Remember that it's an eigenvector, so up to a face, it doesn't matter. So in fact, let's use this guy here. Okay, so YL n minus 1 theta phi is up to a face, which I'm going to just call e to the I delta. Right? This is arbitrary. That is exactly the proof that we need. Okay. So it turns out that you don't need to keep going to get the negative m. So why is that so? And this comes down, this is where you can appeal to the differential equation obeyed by these guys. Right? So it turns out if you look at Jackson, it will turn out that there's a name to these guys. So we have an explicit formula for this. So in some sense, you don't need to know what name, just write it down. But in the literature, this is called the associated Legendre function. Okay. So let me write it down and tell you about the negative m case. So, in the literature, again, up to a phase that you have to check, this is given by e to the I m phi, and then multiplied by PLM cosine theta. Okay, this is called the associated Legendre function. And in particular, when m is 0, you get the Legendre polynomials. Right, so P, L, m equals to 0 gives you P, L, which is the Legendre polynomial. And what I was getting at is that what happens for m negative, right? And so this is where you can appeal to the differential equation to let you recognize that all you really need to do is to actually flip the sign of m, right? And that would suffice. And to recognize that, we need the differential equation. Okay. Of course, I need to find it. Yeah, there we go. Yeah, so remember that you now know how to calculate the Laplacian on the sphere. And you know that the negative Laplacian on the sphere times YLM is just L times L plus 1. Right? Because this is just J squared. Right? This is basically just J squared on the sphere. J squared in the position representation. But you also know that YLM is proportional to e to the I m phi. So in fact, by plugging that in, you will get rid of phi. There's no more phi in the equation. Okay, and so what you can do is basically you end up deriving a differential equation for this guy, which looks like the following. So this would imply, so using YLN proportional to e to the in phi times PLN of cosine theta, what you will get from that is you get the following ordinary differential equation. You can express everything in terms of cosine, so it'll look like the following: d cosine, and then sine squared d cosine PLN plus L times L plus 1 minus, and this is the important part, m squared over 1 minus cosine squared, which is, of course is just sine squared, PLN equals to 0. Right, so this is an ODE in terms of cosine theta. Right, so you use C as your independent variable. Okay, and this is in fact, of course, what you do in Jackson. So in some sense, this is the third way to solve for spherical harmonics. Right? Remember, the first way is to just use the homogeneous degree L polynomials, and you can construct term by term using the x plus, x minus, x3. This is the algebraic way. The algebraic way plus some differentiation, right? The third way to do it is, of course, just solve this equation directly, right? Which some people do. And this you might need also when you, in the event you don't want just L integers, right? Suppose you ever need some other value of L and M, then you have to solve this. But for us, thankfully, this is most of the time this is all we need. Okay. Now, for our purposes here, what's important is to recognize that this is m squared. So therefore, PLM and PL minus M solves the same equation. Okay? So that means what? That means that we should be able to get up to a normalization at most. Simply the same solution by simply flipping this minus m, because minus e to the minus in5 would already guarantee. So it must be that p. So in other words, YL minus m must be proportional to the e to the minus I minus in5 times PLM. Okay? Because it solves the same equation. So it doesn't matter what the sign of m is. So you may as well use the same thing. Right? And this is in fact why many books, I think I'm taking this convention from Sakurai, if I'm not mistaken. So we'll define YL minus m theta phi to be in fact e to the minus 1 to the m, and then YLM complex conjugate. Okay, why complex conjugate? Because of this guy. Why? You see, everything else is real in this expression. So all you do is just use this property over here to flip the sign of m, and therefore you guarantee that you get the right eigenvector of J squared and J3. Right? J3 I think is clear. because j, this is the eigenfunction of j3. But j squared, you've got to appeal to this guy, right? That you can use the same solution to solve the same equation either for plus n or minus n, because the equation only cares about n squared. Okay. Any questions for me? Yeah.
What is the minus?
It's a phase convention. We are asking about minus m. Yeah, it's just a phase convention that we choose, right? So remember the eigenvectors are only defined up to an overall phase. So we can choose anything we want. So, right, the square of this is 1, right? Minus 1 to the m. The square of that is 1. So we are you can call it, you can even say it's negative, right? You can even just say it's negative YLN bar, or e to the I delta, or e to the anything you want. Yeah, that's the definition. That's why I said earlier, have I erased it? Yeah, this guy here, no, this guy. So whenever you solve a problem, make sure you check the phase convention. Otherwise you might run into trouble. Any other questions? Okay. Good. So, I think what I'm going to do is I'm going to talk just a little bit more about rotation operators, and then we should do some applications, and we'll see, especially for the spherical harmonics, that is going to show up repeatedly for the hydrogen atom, for the simple harmonic oscillator. So let's do that. Okay, so yeah, two things. One is about rotation symmetry, and the other one is about spin path, right? So what we're seeing here is an explicit realization of integer spin. And so you can ask the question, what about spin path? Let's do that first. How do you get spin one path? Right. So remember that what we use the algebraic properties of the angular momentum operators to show that in general we have both half integer spin and integer spin. So the question is, how do you get spin 1/2? And this is actually where, this is actually why the Pauli operators are very important. Right? So in a two-dimensional Hilbert space, you can define the following set of operators. Okay, so sigma I, so I is 1, 2, 3. So these are not necessarily matrices, right? If you start from the algebraic point of view, what I like to do is I like to start from the algebraic property that when you multiply these guys, so firstly, let me define them to be Hermitian. Okay, and what you find is that you can start with the property that when you multiply sigma I with sigma j, you get Kronecker ij times the identity operator plus I epsilon ijk sigma k. Okay? And what you can do is that if you choose the basis where sigma 3 is diagonal, you can obtain an explicit matrix representation of all the sigma 1, 2, 3. Okay. Let's see here. Do I want to write that down? Yeah, why not? Let's do that. So in fact, we've seen this before, I believe. So sigma 1. Well, now let me put a sigma hat on top. Sigma hat 1 is given by 0, 1, 1, 0. Sigma hat 2 is given by 0 minus I, 0. And sigma 3 hat is given by 1 minus 1. Okay? So in other words, this is the basis where sigma 3, the operator acting on plus or minus, gives you plus or minus, plus minus. So the eigenvalues are plus or minus. Okay? What's important for us is the following. Let me say this and then we'll take a break. So if you take the, this is just the multiplication rule. But if you consider sigma I, sigma j, minus sigma j, sigma I. In other words, if I consider the commutator, sigma I, sigma j, then that means that I'm taking this guy and I'm subtracting it with the I and j indices swap. So I have Kronecker ij minus Kronecker ji times identity. Well, of course that is 0 because Kronecker delta is symmetric. But what about this guy? I got I epsilon ijk minus I epsilon jik, and then contracted with sigma k. So this will give me, in fact, twice, because this is in fact plus epsilon ijk, because remember that Navier-Civita is completely anti-symmetric in its indices. So therefore this will give me twice of I sigma ijk sigma k. Okay, and so if I divide throughout by 4, what do I get? I get the following. I get sigma I over 2 commuted with sigma j over 2. So I distribute the 4 between them. And then on the right hand side I get I epsilon ijk sigma k over 2. So what I have now is I can now identify these guys, this commutation relation, as nothing but the same commutation relations as the angular momentum operators of the rotation group. Exactly the same, except now my ji is sigma I over 2, and so for example, J3 acting on plus or minus, the same plus or minus here, is now, because of this factor of 2, plus or minus 1/2, plus minus. So this is spin half. Why are the Pauli matrices so important? Because they allow you to construct an explicit representation of spin half angular momentum operators. They allow you to explicitly lay out what it means to have the mathematical description of spin half electrons. Right, so this part, this this angular momentum operators, let me write it down here. Yeah, so Ji equals to sigma I over 2 act on the spinner portion of electrons, muons, taus, and so on. These are the fermions, the spin half fermions in nature, right? Of course, also protons and neutrons and so on, right? So it gives you an explicit mathematical description for spin half objects. So after the break, we'll talk more about these things. Any questions for me? Okay, see you guys in 10 minutes. Oops. Okay, so, but it's okay, everybody is here. Right? So, special means just that it's determinant 1. Determinant of the, in this case, our representation of the rotation operator is 1. Unitary, as you know, just means d dagger d gives me identity, and this is just a 2-dimensional representation of it. Okay, so the main things I need to explain are these two things, because 2 dimension is clear, because this is a spin half system, so it's either spin up or spin down, and that's clearly 2-dimensional. So what about these guys? So in fact, let's first start with the unitary characters here, right? E to the I theta dot sigma over 2, you can easily take the dagger, right? So in fact, we proved the unitary character quite generally, but we in the position representation. But it turns out, and this will be the last thing I will say about it, it turns out that there's no position representation for these guys. So it's very important that we prove the unitary character separately. Because there's no position representation for these guys. So we take the dagger of these, then what will happen is that this will become plus I. Theta is real, these are just rotation angles, but sigma is permission, as we have assumed. So this is just sigma over 2, because sigma dagger is sigma. Okay? We'll use the permission property to construct their representations. So this is important. And also, of course, because they're observables corresponding to spin. Right? And so the spin eigenvalues. So when you take d dagger d, sigma dot theta dotted into sigma obviously commutes with sigma dotted into sigma. So all I have to do is just add them. Plus I theta dot sigma over 2 minus I theta dot sigma over 2. Right? Remember that in general, e to the x times e to the y, you cannot just add the exponents. Right? But in this case you can, because the only difference is a sign. They only differ by a sign. So they obviously commute. And so you can easily determine that they are unitary. Okay. Determinant equals to 1 turns out the following. It turns out that this is a good place to tell you guys about oops, which I don't know if I have told you guys about, but let me just mention it here. If you take the determinant of the exponential of an operator, it turns out to be just the e to the trace of the exponent. So in this case, determinant of e to the minus I theta dot sigma over 2 is just e to the I theta a over 2 trace of sigma a. In other words, it's just sigma dotted into the trace of each and every Pauli matrix. But what is that? Remember that the trace of an operator is just the sum of the eigenvalues. Are you guys familiar with that? It's just a trace of the eigenvalues. But these guys, remember, can be diagonalized, and each and every one of them has eigenvalues plus or minus 1. So therefore, the trace of each and every of the Pauli operator is just plus, plus, minus, which is of course 0. Plus 1 plus minus 1, which is of course 0. So this is in fact e to the 0, which of course is just 1. Okay? This is where the name SU2 comes from. It's a special unitary 2x2 group. And what you are basically learning today is that this group, SU2, is in fact the implementation of rotations, but for spin-half particles, electrons, muons, protons, all these particles are spin-half. How do you implement the notion of rotations for them? Is through the group SU2. Let me write that down because I often say it in words and then people ask me again later on and I realize that it's because I don't write it down. So SU2 implements rotations on spin-half particles, such as protons, neutrons, electrons, positrons, muons, taus, quarks, and so on. Neutrinos. Okay? All the matter. If you're a particle physicist, we call them matter, because all the matter fields in the universe are fermions. Okay. So the last thing I want to explain is why there's no position representation. And this is a very interesting discussion you can find in Sakurai. So I recommend if you have a copy of Sakurai, you should go read it. But let me just summarize the argument. Okay. Yeah. So what do we mean by that? What we mean is that just as we managed to figure out that this is basically YLM, the angular part of the degree L polynomials for integer spin. What about theta phi 1/2? and m, of course, is plus or minus 1/2, right? Does something like that exist? Okay? And so you might think, let's try the same trick, right? How do we derive this? Remember what we did was we took j plus, and then we applied it on the highest eigen vector of m, which is 1/2, 1/2, and you try to solve this differential equation. Right? Remember that this will just be a bunch of differential operators acting on, so this is a differential equation. Solve differential equation. Okay? What you will discover is that you can. There is a solution. The solution is the following. It will give you in fact, let me summarize it as above. If you apply the plus to plus half, it will give you 0. If you apply j minus to the minus 1/2, it will also give you 0. Right? There are only two spin states. So if you try to raise the plus half, it should not give you anything. If you try to lower the minus half, it should also kill the state. So from that, you can show that the states with plus minus 1/2 go something like this. It's square root of sine theta times e to the plus minus 1/2 I phi. Right? So this should not be surprising. All you need to do is solve for this guy. Right? This is not surprising because that's the eigen function of J3, because J3 is just I d5 minus I d5. Right? And so you really only need to solve for theta. So that's the solution. Well, if this is a solution, remember that you have to be consistent with the lowering operator. Okay, so in particular, j minus 1/2, 1/2 must be proportional to 1/2 minus 1/2, which is that with e to the minus I phi over 2. Okay? But what you realize is that if you actually do that, so if you now actually apply j minus whatever differential operator it is, right? I don't have to write it down, but it's basically saying that j minus, now written in terms of theta and phi, now this guy acting on this guy, e to the I phi over 2, right? Remember, this is proportional to theta phi 1/2, 1/2. So it should give you this guy, but with a minus I phi over 2. But it does not. In fact, what it gives you is that it's e to the minus I over 2 phi. That's okay. But the theta part will give you, in fact, cotangent. So it will be, in fact, cosine theta, cotangent, and then divided by square root of sine theta. And this is obviously not proportional. Not proportional. Let me just write not proportional to theta phi 1/2 minus 1/2. So there's a contradiction. Yeah? There's a contradiction because you do not get back. You get an inconsistency, which means therefore is wrong. This prescription is wrong. Yeah. So like I said, I just want to write down the argument, but the detailed calculation, I think Sakurai actually describes it. So you can look at this discussion. But basically, that's the gist of it. You find that you don't get a consistent answer solving it directly versus using the raising or lowering operator do not give you the consistent answer. Okay. So the last thing I want to talk about before I go into discussion of explicit examples, namely the hydrogen atom and the simple harmonic oscillator, is that of rotational symmetry. Right? At the level of quantum mechanics. So what does rotation symmetry mean, especially for Hamiltonians? Right? So rotational symmetry especially for dynamics, means the following. It means that if you have a Hamiltonian, remember that in quantum mechanics, what determines the physics of the system is all contained in the Hamiltonian, because that is what describes time evolution. Right? If you don't have the Hamiltonian, basically you don't know what your system is. So, and vice versa, if you know what your system is, that means you know the Hamiltonian, because it describes all there is to know about what your system does as a function of time. So, you can ask the question, how do I describe things differently if I rotate my space? Right? Or in other words, if I choose a different basis from rotation, right? So H in one frame versus H prime in rotated frame, which is just, in ordinary rotations, this means you take the coordinates and you transform it. But because we're doing quantum mechanics, how you rotate, how you talk about these things is, for example, you can think of this as x prime. This is the matrix element of your Hamiltonian in the position basis in the x frame versus Rx H Rx prime H, right? So this is just two different bases, but this guy we know is equals to X D R hat dagger H. This guy is D R hat X prime. Okay? So if you want to compare doing physics in this frame and doing physics in this frame, basically we have to compare this versus I'm sorry, there's no hat on this. There's a hat on R hat, but not on D. You have to compare D R hat dagger H D R hat. Okay. So rotational symmetry means at the level of the dynamics means that even after you change your basis by rotation, you still have the same Hamiltonian. That's what it means. Means that H is in fact given by D dagger H D. Okay. And usually for any rotations, for any. Okay. If it only works for one particular rotation, then it's not really rotationally symmetric. Right? It has to work for all kinds of rotations. In fact, next semester when we do the Stark effect and the Zeeman effect, that will be an example where the rotational symmetry is broken, because now you have a preferred direction. The preferred direction is given by basically where is the electric and magnetic field pointing. Right? But in any case, this is what we mean by rotation symmetry. But remember, rotations are given by rotations at the level of the operators are given by e to the minus I theta dotted into the generators. So if you work this out, you will find that this is equivalent to demanding that the generators commute with the Hamiltonian. Okay, so this statement is equivalent to this statement here. Okay, so this statement here is equivalent to this statement here, because saying that this guy is invariant under a finite rotation because the multiplication rules are completely determined by the Lie algebra, by the commutation relations. Therefore, it's equivalent to demanding that the generators commute with H. Right? It goes both ways. Okay, and what that tells you is that so I don't have time to talk about hydrogen or I'm not going to start with hydrogen anyway. Let me finish this. Okay, so this has consequences for the degeneracy of your observable. Okay, so for any observable. So here I'm using the Hamiltonian as one of the most important examples. But for any it really works for any observable, any Hermitian H. So it's rotationally symmetric. Then we've already seen in a very general way that symmetry implies degeneracy. Where does that show up? How does that show up here? Let's see it explicitly. Okay. So in fact, we'll see that this is where the n values, azimuthal numbers come in. So suppose I found the eigen. So firstly, the fact that these guys commute with J means that I can use J squared, J3, and H are compatible observables. Okay, this is the key point here. And this will show up repeatedly throughout all our discussions of atomic physics, right, which is a big application of what we're doing here. So once you know that something is rotationally symmetric, because it commutes with JA, you can just choose J3 to commute with this. Or J squared commutes with J3, and because H commutes with all the J's, so it has to commute with J squared as well. Right? So therefore, you know these guys are all compatible. So therefore, I can choose and simultaneous eigenset of H, J squared, and J3. So this will be lambda Ln, J squared. Lambda Ln is L times L plus 1, lambda Ln, and of course J3, lambda Ln is M times lambda Ln. Okay? But now I want to show you that all the n values for a fixed L must correspond to the same lambda. So claim so same lambda for fixed L, but M can run from L to minus L. In other words, there must be at least a 2L plus 1 degeneracy. Okay, so how do I know that? So let's just use the fact, let's just rotate these guys and see what we get. Okay, so if I rotate this guy, let us observe that the rotated version of this guy is also an eigencat. Why? Because it commutes to this guy. So this is just d of h times the cat. But h times the cat gives me lambda. So it gives me back d r lambda lm. And therefore the rotated guy is also the same eigencat as the cat itself. So what I can do therefore is I can now insert a completeness relation here. So because of this, let me just say this, because of this, d of lambda Lm, because of this, I also know that j squared acting on this guy is L times L plus 1 d of r lambda Lm. How do I know that? Because this j squared commutes with everybody. So I can certainly commute this guy through and it'll give me L times L plus 1. So therefore, this guy must in fact be orthogonal to every other state with a different L. Okay, so L lambda prime, L prime, M prime, lambda Lm must therefore be proportional to Kronecker L prime F, because this is an eigenstate of J squared. And remember that eigenstates with different eigenvalues are necessarily orthogonal. Okay, so therefore, in other words, this guy is block diagonal in L space. But once you know that, then you can see that what I'm saying over here, H applied to this guy is, in fact, if I insert a completeness relation here, and let me end that. Sorry, let me just give me 2 more minutes and I'll finish. So H applied to D at the rotated eigenstate. You can first insert a completeness relation, right? Which means you are going to sum over lambda prime, L prime, M prime, lambda prime, L prime, M prime, dr lambda Lm. But we just shown that this guy is block diagonal. It will not, this acting on this will be 0 unless L prime equals to L. So immediately this is only just sum over lambda prime M prime. Lambda prime L M lambda prime L M prime lambda prime M prime lambda prime M prime, but L has to be the same. D R hat lambda L M. Okay? But I know that this has to give me lambda. This applied to this must give me lambda. So therefore, lambda prime must be equal to lambda. And these are just the sum over n prime. Right? These are just coefficients. These are just coefficients depending on n prime. This is just a sum over so we already figured out that lambda prime had better be equal to lambda because we have already shown from here that h applied to this guy has a spit out of lambda. So all of these lambda primes better be lambda, otherwise there's no way I can get out lambda as an eigenvalue. Because these guys are orthogonal. Right? L, n prime, C, n prime. These are just numbers. Okay? So and that's exactly what I want to prove. That is, no matter how I rotate my eigenstate, there are two things that let's write down to summarize. No matter how lambda L m is rotated, it remains an eigenstate of h and j squared. And therefore, there must be a 2L plus 1 degeneracy of h. Because any m, you can see this is a sum over m's, and any m value has to give you the same lambda for h. Right? Because this superposition can be arbitrary. No matter how you rotate it, every state for different m has to give you lambda. The other thing that we'll learn from this analysis is that D, if you create a matrix for this guy, what do we learn about the matrix? You learn that this is a block diagonal. This is number one. Number two is that this guy is block diagonal. So the first little block is a 1 by 1 block where L equals to 0. Why do I say that? Because what we have discovered is that L, M, D, L prime, N prime, L, M is proportional to connector L prime, L, which means that L prime and L must be the same number, otherwise this is 0, which means that you start from L equals to 0. L equals to 0 has only one n value, so this is just a one number. Then you can have L equals to 1, which is now, this is L times 1, 2 times 1 plus 1, which is 3, a 3 by 3 block, which is this block diagonal matrix. And then you have a 2 times 2 plus 1 equals to 5, 5 by 5 block for D. So these are basically D, L equals to 1, D, L equals to 2, and so on. You can keep going. Okay? And this block diagram, if you look at the cover of Sakurai, is exactly what he's drawing over there. Right? It's to show you that the rotation, the representation of the rotation operator, if you put it all together, can be viewed as an infinite matrix with block diagonals where each block corresponds to a particular spin. This is spin 0, spin 1, spin 2, and so on. Okay? Any questions for me? See you guys on Thursday.